Welcome to BioVivacious. BioVivacious is a YouTube channel dedicated to clear fundamental concepts in biosciences. In this series of videos, we are trying to understand photosynthesis. In the previous video, we spoke about fixation of carbon dioxide with the help of Rubisco enzyme, how CO2 get fixed in the living system. At the end of that carbon fixation, what we are getting is a 3-carbon compound which is 3-phosphoglycerate. Our goal is to convert 3-phosphoglycerate into 2 other 3-carbon compounds, and those 2 compounds are glyceraldehyde 3-phosphate and dihydroxyacetone phosphate. This is our goal. And this conversion of 3-phosphoglycerate into these 2 products are known as the reduction. This is the second step in C3 pathway. How do we carry out reduction? Reduction requires 2 important molecules. One is ATP and the second is NADPH. Why do we require these 2 molecules? Because as we know, the 3-phosphoglycerate, it has the 3-phosphoglycerate. In order to convert this into an aldehyde, it requires tremendous amount of oxidation reduction potential, and that is roughly about 0.5 minus 0.5 volt is required. If you look at NADPH, the oxidation reduction potential of NADPH is only about 0.35 minus 0.35 volt. So in order to carry out the reduction of this molecule, we will use ATP, and combination of these 2 molecules will drive the reaction, conversion of 3-phosphoglycerate into glyceraldehyde 3-phosphate and dihydroxyacetone phosphate. Now remember that ATP and NADPH are the end products of the light reactions. Let us see how do we convert this. We will begin with this molecule, that is phosphoglyceric acid. In the first step, this is the first step, it is the conversion of phosphoglyceric acid to 1,3-bisphosphoglycerate. So therefore it is a phosphorylation reaction. Phosphorylation. So the phosphorylation reaction is carried out with the help of ATP molecules. So it is broken down to ADP hydrolyzed and inorganic phosphate is attached there. So therefore we get 1,3-bisphosphoglycerate. This is catalyzed by, the first one is catalyzed by phosphoglycerate kinase. Though it is a kinase enzyme, the reaction is reversible. If you look at glycolysis, now you will find a lot of similarity with the glycolysis that is happening even in this reduction step. Once you have 1,3-bisphosphoglycerate, now the next step is the real reduction step. So therefore here is a reduction step. The reduction step is carried out with the help of NADPH. NADPH plus H plus, that will oxidize to NADP plus. The 2 hydrogens will help to convert 1,3-bisphosphoglycerate into 2 products. The 2 products are, one is glyceraldehyde 3-phosphate, this is glyceraldehyde 3-phosphate, and dihydroxyacetone phosphate. So these are the 2 products. This is DHAP. So these are the 2 products that are formed. Now this is the second step, and the second step is carried out by here I am writing glyceraldehyde 3-phosphate dehydrogenase. It is an NADPH dependent reaction. So this NADPH and ATP molecule is coming from the light reactions of photosynthesis. Now once you have glyceraldehyde 3-phosphate and DHAP, generally this exists in about 96% will be DHAP and 4% is glyceraldehyde 3-phosphate. We also require a third enzyme, and the third enzyme will convert DHAP into glyceraldehyde 3-phosphate or vice versa. This is an isomerization reaction. So therefore, this is third one. So the isomerization reaction is carried out by triose phosphate isomerase enzyme. So in the entire reduction step, there are three enzymes playing a key role. One is phosphoglycerate kinase. The second one is glyceraldehyde 3-phosphate dehydrogenase enzyme, and the third one is triose phosphate isomerase. So at the end of this, we are left with the two products. The two products are glyceraldehyde 3-phosphate and dihydroxyacetone phosphate. Once we have this, it will undergo the third phase of the third phase of the C3 pathway. Generally what happens is, for every carbon dioxide that is fixed, for every CO2 that is fixed, we will require 2 ATP molecules and 2 NADPH. Ribulose 1,5-bisphosphate, fixed carbon, CO2 is attached, we are getting phosphoglyceric acid, and this is converted to triose phosphates. So this is in the carboxylation step, this is in the reduction step. Once we have triose phosphate, the next step is to convert this back into ribulose 1,5-bisphosphate. And this is the regeneration step, which is number 3, the regeneration step. Now, if we have to count the number of carbon atoms, so this is a 5-carbon compound, assume there are 3 such molecules are taking part. So 3 into 5 are 15 carbon atoms. 3 carbon dioxide is fixed. So therefore 15 plus 3, it becomes 18. In other words, this will be 6 molecules of phosphoglyceric acid. Now the 6 molecules of phosphoglyceric acid will give 6 triose phosphate molecules. What will happen is, from the stromal side, this is a stroma, from the stromal side, one of the triose phosphates will get out. Triose phosphate will get out, and that triose phosphate is used for starch production. The remaining, so therefore you are left with the 5 triose phosphates. You are left with the 5 triose phosphate. 5 into 3s are 15, the same number of carbon atoms, we will be getting it back. This is what is going to happen in the third stage, that is the regeneration step.